Welcome to Advanced Math Topics. In this section, we're going to transition away from the heart of algebra and linear topics. We're going to get bent. Probably shouldn't say that, but what I mean by that is we're going to explore non-linear functions, which is the heart of advanced math topics. Polynomials, particularly quadratics, exponentials, circle equations, and more. So with that, let's jump right into it. Let's begin by defining a polynomial. It's a mathematical expression with, as the name suggests, many terms. That's essentially what polynomial means. And what exactly is that? Well, examples of polynomials would be things like x squared, 5x plus 2, 3x cubed minus x. These are all examples of polynomials. What is not a polynomial? Well, 1 over x, or square root of x over x plus x to the negative 2. These are not polynomials. Anytime I'm dividing by x or I have a radical or a root of x, that is not going to be a polynomial. They're essentially just whole number exponents. And in standard form, as we typically call it, on a single variable polynomial, it always goes from the high exponent left to right, x squared minus 5x plus 6. Okay, so how do we actually begin to name and identify polynomials? We do it in two different ways. We do it based off the order or the degree and the number of terms. So if I look at my examples up here, x squared is a degree 2 polynomial. What do I mean by that? In a single variable case, the highest exponent that appears, 2, is the degree of that polynomial. So here I have a 2 in x squared minus a 5x, which is essentially a 1, plus 6, which is essentially x to the 0 power. So my highest degree is 2. This 2 is a degree 2 function. All degree 2 functions, by the way, are what we would call our special case, we're going to spend a good deal of time on later, quadratics. In the case of x squared, there's only one term, so we would call that a monomial. How about 3x cubed minus x? Well, that would be degree 3, and we have two terms, so that would be a binomial. And in the case of x squared minus 5x plus 6, well, that again is degree 2. But we have three terms, so that would be a trinomial. And as we go up in the number of terms, we eventually just use numbers. 4-term, 5-term, 6-term. And degrees, we have degree 2, degree 3 cubics, degree 4 quartics, and so on. Eventually we just, again, use numbers. 6th degree, degree 7, etc. We won't deal with those kinds of functions. I should also mention we could have more than one variable. So how do I think of degree in terms of multiple variables? Well, let's suppose I had x squared plus 5x minus y cubed plus 10. What's the degree of that polynomial? Well, for two different variables or multiple variables, we add the degrees of each. The highest exponent of x is 2. And the highest exponent of y is 3, so the degree of this polynomial would be degree 5. Just like we did with fractions in our basic skill set, let's review how we add, subtract, multiply, and divide polynomials. Start with addition, subtraction. Let's suppose we have the following polynomial. I could distribute and simplify first, so 3 times 5x squared is 15x squared. 3 times 2x is going to be plus 6x. Minus 2 times 3x squared, distributing the next parentheses, is minus 6x squared. Minus 2 times plus 5x is minus 10x minus 10. Now I want to combine like terms to simplify. The x squareds combined, that's 15x squared minus 6x squared gives me 9x squared. And then the plus 6x minus 10x gives me minus 4x and minus 10. I have the answer in standard form, and I've multiplied or distributed it through and combined like terms. How do I multiply polynomials? Well, we know how to distribute a times b plus c equals ab times ac, ab plus ac. Well, we can take that a step further and look at binomials multiplied, something we're going to get used to very quickly here. That might be something like x plus 2 times 2x minus 3. This is essentially distribution twice. I distribute the 2 through the other parentheses and the x through the other parentheses. Oftentimes you might refer to that as foiling. So x times 2x equals 2x squared. X times minus 3 is minus 3x. 2 times 2x is plus 4x. And last but not least, 2 times minus 3 is minus 6. Again, I can combine my like x terms, and those look to be the only like terms, and simplify in standard form. 2x squared minus 3x plus 4x is plus 1x. We don't write the coefficient for the 1, but it's there, minus 6. And that's the answer for multiplying out two binomials. Notice, anytime we multiply two binomials, that results in our typical degree 2 function, a degree 2 trinomial in this case, a quadratic. So to look at it the other way, quadratics factor out into binomials. So can we do that with a little more complicated expression or more terms? Sure, of course I can. I could have, say, x squared plus 2x minus 5 multiplied by x minus 2. And what would I do? I'd multiply the x squared terms by all the terms, the 2x terms by all the terms in the other parentheses, and the minus 5 by all the terms in the other parentheses. I'm not going to bother to multiply that all out now, but hopefully you get the idea. Last but not least, how do I divide polynomials? Well, that gets a little more interesting. There we're dealing with rational expressions, as we call it, and that gets a little more complicated. We'll save that for later. It's worth taking a moment to see how polynomials are graphed. For example, y equals x squared, perhaps our most basic quadratic. That simply is a parabola. All polynomials graph into this U-shaped curve we call a parabola. What about y equals x cubed? You should be familiar with that as well in general. And that graph looks more like that. Notice odd functions for positive values will go up to the right starting from below. Even functions that are even exponents will start high, come down, and then come back up in that case. And we could vary that as we continue with x to the 4th, x to the 5th. It'll be the same basic structures. X cubed minus x, that variation might look something like this, the same shape. I'm trying to get that to go through the origin, but not quite. So terribly drawn, I apologize. And that's how we think about basic polynomials. Might also want to understand how the non-polynomials, y equals the square root of x, y equals 1 over x are graphed as well. Y equals the square root of x would look something like that. Notice there are no negative values of x that apply, or negative values of y, and it doesn't accelerate upward. It kind of flattens out as we go. Y equals 1 over x is this interesting shape. As x goes really, really large, 1 over x goes towards 0. And as x gets really small, the y value goes infinitely high. So for positive values, it looks like that. And for negative values, it would look something like that. Now I'm just quickly trying to introduce some of the shapes in the graph so you get used to it when you see it. In many or most cases, the exam will introduce what we call function notation. Y equals f of x, as expressed here. Essentially, f of x is our y value. We might be used to thinking of our coordinate system as y versus x, but now we can think of it as f of x. The y equals the f of x. So what is a function? A function essentially takes an input, an x, into our, call it our little black f of x function box, and it spits out a y value. The unique thing about a function is for a definitive x, there is a definitive y output. There cannot be multiple y outputs from a single x. That would not be a function. That would mess things up a little bit because we'd have many outputs. Well, there are curves that are not functions. For example, a circle would not be a function. If I have a particular x value there, I actually have two y outputs. and it would therefore fail what we call our vertical line test, which is a quick way to graphically check for a function. If I looked at my f of x squared graph, say a parabola, or 2x plus 5, f of x equals 2x plus 5, a line, we can see those functions always pass our vertical line test. There's always over the all x values where the graph exists, our domain as we call it, there's only one intersection with the graph. So that's what a function looks like. In many cases, the difference between y and f of x is that f of x adheres to the function rule. There's a definitive output for a definitive input, and you pass the vertical line test. So how does that function notation work? Let's take the case of f of x equals 2x plus 5, for example. What would f of 3 be? This essentially means if my input x equals 3, my function box will work on it. It will take x, multiply it by 2, so 2 times 3, and note the parentheses here actually means multiplication, whereas here this is our function notation. This does not mean f times 3. So 2 times 3 is my function plus 5. That equals 6 plus 5, or 11. So the output when I input 3 into the function will be y equals 11 in that case. I could look at that for f of x equals x squared. Again, let's say I said f of 5 equals, well, I'd plug in 5 for x. That would be 5 squared, which is 25. So that's the basics of how function notation works. You input the x value, and given the expression in the black box, we output the y value. Let's look at a couple more variations so we get more comfortable with function notation. So if, for example, I had f of negative 2 in this case, that essentially means put in negative 2 for x in the 2x squared minus 5 function. So it would be 2 times negative 2 in parentheses, I always substitute in parentheses, squared minus 5. So negative 2 squared is 4. This becomes 2 times 4 minus 5, still following my PEMDAS rules. 8 minus 5 is 3. The output for negative 2 input to my function, the f of x defined above, 2x squared minus 5, is 3. Well, what if I had an input of f of 2x? What would that look like? That might be a little confusing. Well, again, function notation means I put in 2x everywhere for x in my function. So that means it's 2, double my input, which is 2x, then square it, really square it, then double it by PEMDAS, and subtract 5. What does that equal? Well, 2x squared, be careful, 2x squared is not just 2x squared. 2x squared is 2 squared x squared, which is 4x squared. That's a typical mistake students sometimes make. So this becomes 2 times 4x squared minus 5. That's 8x squared minus 5. This is the answer. This is the output for my function when I input 2x. Notice my output is also a function of x. Don't be confused by that. Let's try a different function notation case. What if my function notation originally was f of x minus 1 equals 2x squared? Okay, this is interesting. So if my input is x minus 1, my output is basically a function of x, one higher than my x minus 1. So what does that mean f of 5 is? Well, that means my x to get 5 as my input means x minus 1, that's my input according to my function here, must equal 5. That means my x is really 6, because that's what I have to plug into my function over here. So f of 5 really is 2 times 6 squared, which is 2 times 36, which is 72. Note the difference between the x minus 1 input and the x used in the function. Not clear on that? Let's take the same function one more time and try entering f of negative 2. What would that be? Well, if x minus 1, the input is negative 2, that means our x that we're working on in our function really is minus 2 plus 1, or minus 1. So then my function then becomes 2x squared is really 2 times minus 1 squared, which is minus 1 squared is 1, so 2 times 1 is 2. That would be my output for f of negative 2 put into this function here. Note, just as we add, subtract, multiply polynomials, our functions can define polynomials. The functions themselves can be added, multiplied, subtracted, and even embedded. Let's look at the case of addition. What if I have two functions defined as f of x equals 2x, g of x, another function, equals x plus 1? What is f of x plus g of x? Well, that's kind of like adding two polynomials. It's f of x is 2x plus my g of x, which is x plus 1, and I combine the like terms. The answer is going to be 2x plus x is 3x plus 1. I just add the different functions and their polynomials. What about multiplication? F of x we know is 2x times g of x is times x plus 1. Now I'm essentially multiplying the polynomials, and we saw how to do that earlier as well. It's 2x times x, which is 2x squared, and 2x times plus 1, which is plus 2x. What about embedding functions? What exactly is this notation right here? This means f of, and the input would be g of x. So it's a function within a function. Let's start with the inner function first and work from there. G of x is x plus 1. So this is f of x plus 1. Okay? And what is f of x? Well, we know f of x is 2x, so 2 times the input. So f of x plus 1 must be double the input, x plus 1, so 2 times x plus 1. I could multiply that out and simplify. The result is 2x plus 2. So f of x, g of x, that embedded function, is 2x plus 2 given my original functions. So now that we know something about polynomials and functions and how they interact and add and subtract and multiply, let's discuss the concept of root zeros, x-intercepts, or solutions before we get into quadratics. The roots or zeros of any polynomial is essentially where that graph crosses the x-axis. So we're going to get into the idea of looking at cases where f of x equals 0. What x values give me a 0 y output? We can think of that as y equals 0 or f of x equals 0. So what does that mean? In a quadratic, say y equals x squared type function, we intercept the x-axis at two different points, as we can see. Those are what we would call our zeros, or our roots. That could be true of a cubic function as well. I might have this root, or as we saw in like x cubed minus x, I might have 3 different intersections of the x-axis. There would be 3 roots. Even lines have zeros or roots or x-intercepts, as they really are. If I drew a line as such, right here would be my x-intercept of the line, where my line equals 0. So maybe that's y equals x plus 2 at y equals 0. We can solve for that 0. It's x plus 2. X equals negative 2. We know the 0 occurs there at x equals negative 2. So anytime we're trying to find the roots, the zeros, the x-intercepts, or loosely called the solutions, we're talking about essentially the same thing, where the graphs cross the x-axis and intersect. And the conditions for that is always y, or f of x, equals 0. Much like when we find the y-intercept, we plug in x equals 0, the equation of the y-axis, to find a y-intercept on any function. Here we're finding the x-intercepts. So there's a very important fundamental theorem, the algebra theorem, related to that. Any n-degree polynomial has exactly n roots. What does that mean? Well, my quadratic here is a degree 2 function. It has exactly 2 roots. A cubic function, degree 3, has 3 roots. A line, which is a degree 1 function, has 1 root. Likewise, if I had a 5th degree or degree 5 function, it would have 5 roots exactly. So note, any n-degree polynomial has exactly n roots. Now you might step back and say, wait, I know a little bit about quadratics already. Sometimes I have 0 intersections or just 1 intersection with the x-axis. That's true. The algebra theorem does not differentiate between real roots, which are actual intersections of the graph and the x-axis, and the possibility of imaginary or complex roots. So I don't always have n intersections with my x-axis. I'm going to have at most n intersections, and I could have some measure of complex roots which come in pairs as well. So there could be no real roots. There could be a combination or mix of real roots and complex roots, or entirely real roots, and we'll have to figure that out. We'll see how that works in the case of quadratics as we proceed. Okay, and now we finally dig into quadratics, our degree 2 polynomials. The quadratics for the test come in basically 3 formats that you should know and be aware of. Our standard form, ax squared plus b x plus c, where a, b, and c represent constants, numerical values. We're going to learn how to factor those standard form equations into binomial factors, which essentially are intercept or a factored form, where a, again, is the very same a coefficient in our standard form. And by the way, the sign and magnitude of that represents whether our parabola will be upward opening, narrow, or wide. If it's positive, it opens upward. Negative opens downward. If it's a large number, it will be very narrow in shape. If it's a fractional number, really very wide. The other constants here are m and n, which are generally our roots or our factors, as we just mentioned in the earlier lesson. The third form is the vertex form. Again, the a is that same constant that indicates the shape and direction of our parabola, and hk in this case represent our vertex. We'll come back to each of these forms. We're going to start with our standard form, and as most classes do, we'll start by trying to solve for the zeros, the roots, the x-intercepts, or solutions by factoring our standard quadratic into factored form and take advantage of the zero product property to find those roots. So how do we go about that? Well, I'm going to start with this simple case first. My leading coefficient a equals 1. That might be something like x squared minus 5x plus 6. How do I factor that? I'll look at the factors of 6, call that xy, that add to the coefficient of the x. So the factors of my c that add to the b. So in this case, x plus y would equal minus 5. So what are those? What factors of 6 are there? There's 1 times 6 and 2 times 3. Do either of these sum to 5? Well, minus 6 plus 1 sums to 5. The only problem, that multiplies out to negative 6, not plus 6. Alternatively, minus 2 and minus 3 multiply out to plus 6, and they add up to negative 5. So our factors here in our simple factoring case are going to be x minus 2 times x minus 3. We don't really show it, but our leading coefficient here is 1. This is the simple or a equals 1 case, and we'll just label that our simple factoring case. Okay. So how do we solve for the roots? Well, we set that function value equal to 0. And we take advantage of the zero product property. If that parentheses evaluates to 0, the whole equation is true. So x minus 2 equals 0, and solving for that, x equals 2. 2 is the root or x-intercept that's associated with the factor x minus 2. Likewise, if this parentheses evaluates to 0, 0 times anything equals 0 makes our equation true, And we can solve the simple equation case thanks to our zero product property. X minus 3 equals 0. X equals 3. Don't forget that sign change between the factors and the roots. That appears on the exam throughout, and there are opportunities to make sign errors throughout as a result. So what does that mean our quadratic will look like? Well, roughly we know we're going to have a quadratic, if that's my x and y axis, that's going to pass through the points 2 and 3 on our x-axis. It's opening upward, plus 1, so it's going to look something like that. And by the way, plus 6, if we plugged in x equals 0, we get our y-intercept. So essentially our c value in the standard form represents our y-intercept. In this case, that's plus 6. So our graph would pass through plus 6. I'm getting into a little information extra on the graphing here, but let's stick to focus on finding our roots or our zeros. In this case, it's 2 to 3. That's our simple factoring case. Let's try another quick example of that. F of x equals x squared plus x minus 56. So I need to find the factors. In this case, I'll call them p and q, not to confuse them with our variables. And they must sum to p plus q, the coefficient of x, which in this case is 1. It's not shown, but it's 1. So what factors could that be? Well, 56 is 1 times 56, 2 times 28, 4 times 14, 8 times 7. And right away, I see a sum or a difference of 1 with 8 and 7 that multiply out to 56. I just have to worry about the signs. I need a minus 56 and a plus 1. So that's going to be plus 8 and minus 7. My factors for this f of x are x plus 8, x minus 7. And I'm going to set that f of x or y value equal to 0 so we get the intersection with our x-axes. Note, if you're unsure, you should always check by multiplying or foiling out your factors. X times x is x squared. X times minus 7 is minus 7x plus 8x. That's plus 1x. Good. 8 times negative 7 is minus 56. That checks. I did factor that correctly. So that means my roots here are x equals minus 8 and x equals plus 7. Note the change of sign because I'm essentially using my zero product property to make x plus 8 equals 0 and x minus 7 equals 0, both of which will solve this equation. So now I have my x-intercepts or my roots. What if our leading coefficient a does not equal 1? This is what I'll call our more complex factoring case, and I'm going to use the approach factoring by grouping. I like that for a few different reasons. It sometimes takes a little longer. There are many methods, box methods. I can go on and on. You can learn any of them that you want. I'm going to go through the grouping method. Feel free to use your special method. So how does factoring by grouping work? Well, it's the same original idea. I want the factors of not just c now, but I want the factors of c times a. It's what we really did in this simple case. It's just there we were multiplying by 1 when we multiply by a. So I want the factors of AC, let's call those P and Q again, such that P plus Q adds up to that coefficient of X equals the B. Okay? So in this case, what would that be? It would be 6 times minus 6 times 2, which is minus 12. So I need the factors of minus 12, which are going to be essentially 1, 12, 2, 6, 3, and 4, such that they add up to plus 1. The 1 is not shown, but that's what I want the P and the Q to add to. So that would be, well, it's going to be 3 and 4. That has a difference of 1. There's no other way I can create a sum or difference of plus 1. That would be plus 4 minus 3. Okay, great. That's fairly analogous to what we did in this simple case. Now I'm going to set it up a little differently. I'm going to break my 3-term polynomial into 4 terms. I'm going to take that middle plus 1x term, and I'm going to break it out into my plus 4x minus 3x, the two different factors. And I'll just continue to repeat the 2x squared and the minus 6. This is essentially the same or equivalent polynomial to the one above. And of course, we ultimately set that equal to 0 if we're looking to find the roots. So what do I do at this point? I'm going to group. That's the factoring by grouping. So how do I group? I'm going to group there. And I'm going to group, be careful, the minus 3 is plus, these are not multiplying x at this point, plus the minus 3x minus 6. Some students make that mistake and therefore don't like grouping, but it's really something simple to keep track of. So what do I do? After I've grouped, I'm going to factor a 2x out of 2x squared plus 4x. That gives 2x outside the parentheses, leaving me x plus 2 inside the parentheses. Again, you can multiply them back out to make sure you get the original parentheses. On the second parentheses, I'm going to factor out of a minus 3x and a minus 6. Well, I can't factor out x's on both, but I can factor out a minus 3 on both of the numerical values. So I'll pull out the minus 3, leaving me in parentheses x plus 2 again. Now, very important, those parentheses terms must be the same for factoring by grouping to work. If they are not the same, that means you made a mistake, most likely, or your teacher gave you a quadratic that is not factorable over the integers. So what does that become? At this point, the x plus 2 is my common factor that I'm going to pull out. Yes, a common factor does not just have to be a variable. It can be a more complicated expression. So I'm going to factor out my x plus 2, and that leaves in the next parentheses that I'm multiplying by now just the 2x and the minus 3. So 2x minus 3. I factored my quadratic. My factors are x plus 2, 2x minus 3. Set each equal to 0, and we get x equals minus 2 and x equals plus 3 halves. Again, note the change in sign. Those are the two roots or solutions to my quadratic that I've factored by grouping in this case. Let's try another example quickly to see that, because I know this takes some repetition to get used to. So again, in this case, my leading coefficient is not 1. It's actually minus 6. So the first things first that I want to do usually is set my f of x equal to 0 if I'm solving for the x-intercepts or my zeros. And instead of going right to my binomial factors, or factoring by grouping in this case, I'm going to always try to pull common factors out first. In this case, 6, 15, and 36 all have a common factor of 3. In fact, I'm going to pull out the negative 1. I usually want to make that leading coefficient positive. So I'm going to factor out the negative and the 3 common factor here, leaving me in parentheses 2x squared minus 5x minus 12. So the quadratic in the parentheses will have the same roots as my original quadratic. Slightly different graph, but the same roots. So I can use this method and find the roots by continuing to factor this quadratic, which, by the way, is still not an a equal 1 leading coefficient. So I'm going to use factoring by grouping within the parentheses. So 0 equals minus 3. That's the same. And what I'm going to do, I'm going to factor out 2 times minus 12, so the factors of minus 24, the a times the c, such that they sum to minus 5. Well, what are those factors? It's 1, 24, 2, and 12, 3 times 8, and right there I'm done. I see 3 and 8 have a difference of 5. So I think I can set up these factors. It would be minus 8 and plus 3 will give me minus 5 and multiply out to negative 4. So now I can go ahead and begin my factoring process. So for by grouping, I keep the 2x squared. I break apart my minus 5x into two separate factors, the minus 8x plus 3x. And by the way, it doesn't matter what order I put these in. I could have reversed those. And of course, I keep the constant. The result is this 4-term polynomial is exactly equivalent to my 3-term polynomial above. So what do I do at this point? Well, I group. So let's rewrite the rest. Notice I've grouped into two separate parts my polynomial. It's from here that I'm going to find common factors. So between 2x squared and minus 8x, I can factor out a 2x, which leaves me just x minus 4 in parentheses. From 3x minus 12, I can factor out no x's, but I can factor out a common factor of 3. So that becomes 3. Leave me in parentheses x minus 4. And of course, these values in parentheses must be the same if I'm going to be able to factor this. Okay? Next step is I factor out the x minus 4 itself, that binomial, leaving me in the next parentheses my 2x plus 3. And I've factored this quadratic. The roots are x equals 4 and x equals, in this case, minus 3 halves. Why is it minus 3 halves? Because remember, I'm setting each of those individual parentheses equal to 0. Subtract 3 from both sides. 2x equals minus 3. Divide 3 by 2. X equals minus 3 halves. You're always changing the sign between your factors and your actual roots or x-intercepts. Now, why do I like the factor by grouping method? Because in cases where we have 4-term polynomials with a higher degree, in other words, they're not just quadratic. So if I have higher order 4-term polynomials, I generally use factor by grouping as the go-to method to factor them, assuming they can be factored, which is nice because this then applies not to quadratics, and you will see problems on the exam where you'll have to do this. So again, I'm going to start off by our typical grouping. It's the same method. It's almost as if I already broke my quadratic into 4 terms. Now I find my common factors within the parentheses. So the 2 and the 3, no common factor, but I can pull out a y squared, leave me 2y minus 3 in that parentheses. In the next parentheses, between 18 and 27, I can pull out a 9, and I cannot pull out any variable, so that'll be plus 9, leaving me 2y minus 3. Again, I'm always checking that I then end up with the same expression in parentheses. I do, because then what I have to do is factor out the 2y minus 3. So assume we're looking to find the zeros or x-intercepts here. I'd set the function equal to 0. And now I'm going to factor out my 2y minus 3, leaving me in the next parentheses my y squared plus my 9, which means I have the factors 2y minus 3 equals 0. So y equals 3 halves. Y squared plus 9, that's an interesting one. Those are not going to be real roots. So remember, this was a degree 3 polynomial. I'm going to have 3 roots according to my algebra theorem. They may or may not all be real roots or actual intersections with the x-axis. I will intersect the x-axis at y equals 3 halves, but the y squared plus 9, when I set that equal to 0, will not actually be a real root. It's y squared equals negative 9. The root there, if I take the square root of both sides, will be y equals plus or minus 3 times I, which is the square root of negative 1. So I actually get 2 complex or imaginary roots rather than real roots in this case, and they come in pairs. That's expected. Note, if I did end up with something like y squared minus 9, we did in this case as one of my factors broken out, I can jump to the difference of 2 squares or some other special factoring case and continue to work on that or factor that further. In that case, it would be y plus 3 times its conjugate y minus 3. In other words, the point here is after you do this factor by grouping on the first step, you might find you can factor one of these parentheses even further, ultimately giving you 3 real roots or 3 intersections. So I like the factoring by grouping method as a result. If we want to get really good at factoring, let's look at a few strange cases as well. Note, this polynomial looks like a quadratic, but they're not actually quadratics. This is a degree 4 polynomial here. Nonetheless, if it walks like a duck and quacks like a duck, I could probably treat it like a duck. It kind of has a structure much like a quadratic. The exponents are halving as we go down until we get exponent of 0. So 4, 2, 0 is the same ratio as 2, 1, 0 exponents on a real quadratic. That means I can do some clever substitution here. I could essentially treat x squared as my variable x. So this would become x squared, and now I can go about factoring. What factors of minus 8 would then be a simple case, factor into or sum to minus 2. Well, the factors of 8 are 1 and 8 and 2 and 4. So I can do x squared minus 4 and x squared plus 2. Multiply that back out. That gives me x to the 4th minus 4x squared plus 2x squared is minus 2x squared. Minus 4 times 2 is minus 8. This works. Notice I just treated the x squared as kind of my x essentially. Okay? Well, I can factor this further if I notice. X squared minus 4 is again that difference of two squares. So this becomes x plus 2, x minus 2. The things that are being squared, I multiply the conjugates. And x squared plus 2, well, that's not going to be real roots anyway. So the degree 4 polynomial, I have 2 real roots, and I have 2 complex or imaginary roots in this case. Note the factors x plus 2 and minus 2 correspond to x equals negative 2 and x equals positive 2, x-intercepts respectively. Okay, let's look at another important case in the scheme of things to be aware of. Let's suppose I had 5x squared plus 10x plus 6. So I can't find any common factors here to pull out. I'm going to have a leading coefficient here that does not equal 1, so I'm going to factor by grouping in our case. Again, remember, you can use box method, any methods you want if you choose. And there I would want the factors of 5 times 6, the a and the c, that is 30, such that they add to 10. So those factors, p plus q, would somehow equal the 10 coefficient. So what are the factors of 30? It's 1 times 30, 2 times 15, 3 times 10, 6 times 5. That's it. Are there any factor pairs where the sum or the difference is 10? Uh-oh, there aren't. This is not factorable over the integers, as we would say. That's a problem. Wait a second. We spent all this time learning how to solve quadratics by factoring, and we realize it's not a universal solution. Sometimes I simply cannot factor the quadratic over the integers if I have irrational roots or complex number roots, as we'll later figure that out. So what do? Well, practically in the SAT exam case, if you can't factor a polynomial or quadratic quickly, go right to your quadratic formula. That's the answer for you on the SAT, what you should do. And that should happen very quickly. So you either factor it very quickly or you jump right to the quadratic formula. If we can't solve the quadratic by factoring, we need another method. One option for that other method is to complete the squares. So if I started with x squared plus 5x minus 6, and this is something we already can factor. I'm just showing this to show that we get the same answer by completing the squares. This one we already might know factors into x plus 6 times x minus 1, and the roots or zeros are x equals negative 6, x equals 1. We'll keep that in mind as we go ahead and factor. So how do I complete the squares on this quadratic? Well, first things first, I want to set up x squared plus 5x plus some missing number to essentially be a perfect square. I'm going to take advantage of my knowledge of what a perfect square factoring case is. So a perfect square factor is x plus, say, a squared, we know is going to be x squared, square the first, double the product of the two, 2ax, and square the last, plus a squared. So if 5 is essentially my coefficient of x, it's 2a, and I want to put in a number that's a perfect square that ultimately will give me this perfect square term, I know I have to essentially have the coefficient of the x to make it a. By the way, that will be what the perfect square is. It'll be x plus that a. And then I square that number, a, to put that back into my standard form quadratic to essentially set up what's the equivalent of the perfect square. So in this case, I'm having the 5, and that will give me 5 halves. So I know my perfect square is going to be x plus 5 halves squared. And to fill in that extra amount that is the perfect square equivalent, I need to square that 5 halves, so it'll be 5 squared over 2 squared, or 25 fourths. Now, if I add 25 fourths to the expression, I have to subtract 25 fourths from the same expression, so there's no change in the value, and that's maintaining my minus 6, which was originally there. Okay, so now what can I do? I can take all the extra stuff I have, subtracting the 25 fourths and my original minus 6, and keep that off to the side as a constant. Note, this 25 fourths I'm using to create my perfect square. So I'm using that as part of my standard. I'm not going to keep that off to the side. So minus 25 fourths minus 6, which is, by the way, minus 24 fourths, gives us minus 49 fourths. Now I have essentially a perfect square. I've created what we'll later learn is a vertex form of the equation. So how do I work to solve this? Well, if I had set this function equal to 0, I could go ahead and solve. I know x plus 5 halves squared equals 49 fourths. And I'm going to take that up here just because I'm running out of a little space. I'll change the color so it's easier to see. And what I want to do at this point is take the square root of both sides. That leaves me x plus 5 halves on the left equals, now remember the square root of x squared is the absolute value. So technically I'm going to have on the right side plus or minus solutions of the square root of 49 fourths, which is 7 halves. Now I'll subtract 5 halves from both sides. X equals minus 5 halves plus or minus 7 halves. And that turns out to be x equals minus 5 halves plus 7 halves is 2 halves, or 1. Minus 5 halves minus 7 halves, my other solution, is x equals minus 12 halves, which is negative 6. Look at those solutions. They're exactly the same as what we got from our factored case. Complete the squares gets us to exactly the same answer. Why does this work, if you're curious? Well, essentially, you are setting up a perfect square on one side of the equation so you can take the inverse of that function like we've done so many times before in our basic algebra skills. Note, this is a universal solution. In essence, it's one way I could derive my quadratic formula. Not the only way, but it is one way. Let's see that as follows. Let's start with our standard form quadratic, and we're not defining the a, b, and c variables. We're going to solve for x in terms of those constants. So whatever constant we choose to put in there, we're going to get a solution if we set f of x equals to 0, our typical approach. Let's complete the squares on this. So when I complete the squares, I usually like to make my leading coefficient 1. So I'm going to divide through on both sides by a. And that leaves me 0 equals x squared plus b over a, x plus c over a. I'm going to complete the squares, but I'm going to take my c over a to the other side. I'm going to switch this around too. I'm going to make it x squared plus b over a, x plus some missing amount will equal minus c over a, the constant term on the other side now. And of course, if I add the box, the missing amount on the left, I got to do it on the right to keep things balanced. And I'm going to go through my process of taking half the coefficient. That's going to be b over 2a, and that's going to be my perfect square because I know this format of a perfect square. And the missing amount, I will square that b over 2a, so I'll get b squared over 4a squared. Okay? And of course, I need to add that over here, b squared over 4a squared. And now I'll have the following. I'll have b squared minus, well, let's put these, I've got an addition or subtraction of fractions. I want them over a common denominator. So b squared minus, I want to make the a denominator become 4a squared. So I'm going to multiply by 4a times c to adjust for that, so the whole statement can be over 4a squared. Now I have a constant on the right, messy constant, but that is a numerical value, and I'm going to take the square root of both sides. What happens when I do that? I'll get x plus b over 2a equals plus or minus the square root of b squared minus 4ac. Not much I can do to simplify that under the radical, but the square root of 4a squared on the denominator becomes 2a. Notice this is the same denominator over on the left side. X equals minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. There you go. That's it. That is our quadratic formula, our universal solution. And we just got there from completing the squares, which means completing the squares is essentially the same as the quadratic formula. So if I plug in the quadratic formula, I'm really completing the squares. I find it easier in many cases practically. So let's look at that quadratic formula again. Very important you memorize it, but I also want to look at it so we can kind of understand what it's saying about the solution to a quadratic. We're talking about the solutions to a parabola where we cross an x-axis. Note a parabola is symmetrical around its axis of symmetry right in the middle, which passes through our vertex, the minimum or maximum point we typically refer to as h comma k, the vertex. What the quadratic formula is telling you is this center line is x equals minus b over 2a. That is my axis of symmetry. So if I have a standard form quadratic, let's go right back to x squared minus 5x plus 6. I can very quickly get my h value of the vertex, or that axis of symmetry. It's opposite of b, so it's opposite of negative 5 in this case, which is plus 5, divided by 2 times a. A here would be 1. That's divided by 2. My axis of symmetry would be plus 5 halves for that standard form quadratic. So this is essentially my axis. What does the second term mean? This plus or minus b squared minus 4ac over 2a. Well, we know it's just one term that's being added and subtracted. So what that really means is our zeros start at the center line, and we go up some fixed amount, plus, defined by that second term, and we go down the same fixed amount defined by that fixed second term. And it's interesting here is this second term, if you notice, is driven by the expression in the radical. That's why this has a special name. We call it the discriminant. And if we think about it, if that discriminant is a positive real number, the square root will be a positive real number, and we'll go up and down a real amount, and we'll have two distinct real intersections. If that discriminant evaluates to 0, b squared minus 4ac equals 0, we'll go up and down 0. What does that mean to go up and down 0? It means you stay on the axis of symmetry. You'll have only one intersection with the x-axis. By the way, that occurs when my quadratic is a perfect square. Last but not least, what happens if that b squared minus 4ac term is negative? The square root of a negative is imaginary. I'll end up with a complex root. Remember, we had trouble with that when we were factoring. The graph exists in that case. It might look like this, floating above the x-axis or below the x-axis, but never intersecting the x-axis. So this is a very important part of the puzzle. Our discriminant, that second term, tells us how many real roots we have. Let's write this down again. So b squared minus 4ac, that discriminant, if it's greater than 0, I have 2 real roots. My graph looks like the graph shown. If b squared minus 4ac equals 0, I've got 1 real root. My quadratic in that case would look something like that. It touches the x-axis once at the minimum or maximum point and then goes back up or down. It doesn't cross through the x-axis. And if b squared minus 4ac is less than 0, I have no real roots. My graph is floating essentially above or below the x-axis, never intersecting. What we will get are what we call complex roots. That's a number in the form of a plus or minus bi, where a and b are real numbers, I is our imaginary number.